I'm Nigel O'Dea, founder of OB2B Industrial Marketing and PR, which specialises in marketing metals, engineering plastic and composite materials, and manufacturing capabilities across the supply chain. One of the most exciting things to promote is new innovations in design, which is why I'm delighted to be sponsoring this award and to announce the 2020 winner of this category is the Ford Motor Company and its partners for the Chassis project.
Hi, my name's Alan Banks from Ford. I'd like to present to you today the project called Composite Hybrid Automotive Suspension System with the Innovative Structures, as we call Chassis. So the introduction to this project is that we wanted to put mass production into composite hybrid materials for a front suspension subframe, lower control arm and dead beam for a Ford Transit van. This has a volume of around 500,000 vehicles a year. Our target was to spend no more than $9 per kilo for every kilo weight saved. The cycle time had to be under 5 minutes to meet that full production time, and our target was a 40% weight reduction on an average of those three components. Our technical challenges being stiffness, strength and the full vehicle design verification. So the steel parts you can see at the top, the front subframe on the left, the lower control arm in the middle, and the rear dead beam for a front wheel drive vehicle on the right hand side, and the renditions of the hybrid parts underneath. These are a mixture of composite materials and aluminium. So our optimization is obviously key to the project, as well as saving weight, which is the point of this exercise. When you produce composite materials, you also reduce the amount of parts you need to make up an assembly, or that's an opportunity anyway. So you can see that in this case, the rear dead beam saved half of the components that would normally go to make the steel part. The front lower control arm saved 2 of the 5 parts that go to make it up, and the front subframe saved around 2/3 of the parts that it would normally make to make the steel part. So the front subframe is a hybrid of materials, as we've said. So we have high pressure die cast aluminium side rails that bolt onto the body and bolt the lower control arm on. Then we have carbon SMC on the front panel, and aluminium extruded rear panel at the back, and then we have carbon pre-preg upper and lower panels that make up the bulk of the material. The front lower control arm is a mixture of 3 different materials. So we have an inner core, which is made of PA12 with long glass fibre reinforcements. That's moulded separately and then placed into the mould, where it's then over moulded by PA12 with long fibre carbon. Hence it's black on the outside and it's white on the inside. As well as this, we have a steel insert that goes to take the lower control arm ball joint taper. That's all pre-machined before assembly, and that's over moulded by the PA12 long glass fibre, and then completely over moulded by the carbon at the end. The rear dead beam is a protrusion of 3 different materials. So we have a triax carbon, we have UD glass, and we have a woven carbon on the outer shell. That's mounted back to back, as you can see on the picture on the right hand side, and then we have aluminium extrusions that hold the wheel bearing carrier, the spring seat and the jounce bumper reaction plates that are then structurally adhered to the main structure. We also have an aluminium extruded bracket for the shock absorber attachment. So we have we've done quite a lot of work on the life cycle analysis of this, from the cradle to the grave, which we believe is pretty accurate from the data that we have. So the front subframe, we get payback in CO2 of the vehicle in around 3.35 years. That's mainly due to the fact that we're using pre-preg carbon on the upper and lower panels, which is quite energy intensive to produce, as well as aluminium and then the structural parts that we have on that part. The front lower control arm, we get payback in 1.3 years. That's mainly because of the glass material that we use, and we're using PA12 material rather than epoxy on this part, and so we get payback really early in the life of that part. The rear dead beam is even better. We get a payback in CO2 after 0.65 of a year. This one is mainly due to the fact that although we are using quite a lot of glass, we are using carbon in 2 places on this part, but we save quite a lot of weight on this part as well, so hence we get payback a little bit earlier than that. So this is the summary of the project. So our steel parts are on the left hand side, as you can see it, and our composite hybrid parts are on the right. So as you can see, we've saved 44% of compared to the 40% weight saving that we were going after. That equates to 30.6 kilos compared to the standard steel parts. You can see that where these parts are mounted on the underbody, so to the left of the picture in plan, you can see the front lower control arm with the subframe, and on the rear you can see the dead beam axle. So in conclusion, we've met our 5-minute cycle times for all 3 components for the full vehicle assembly off of production tools. We've achieved our average 40% weight targets compared to the original designs. We've got a 56% reduction in the number of parts to make up the end assemblies. We've got really good CAE process for the topology and the optimization processes which were developed sort of during this project. Our manufacturing simulations predict that the parts will be stable with full vehicle integrity, so the warpage and the shrinkage that we get is well within the tolerances to mean that the vehicle and test conditions can maintain. All the components achieve their CAE targets. We start to do testing correlation for all these parts in early 2021, COVID notwithstanding, and all of our costs are fully met in strict adherence to our $9 per kilo cost target. Thank you very much. That's our project. If you have any questions, then please contact us on the details on the slide below. Thank you.